Hello everyone, my name is Xuanqi Guo. I'm a PhD student at UIUC, working with Professor Sibi Mohan and Tianying Xu. Today, I'll present our work, Set the Configuration for the Heart of the OS, on the practicality of operating system kernel debloating, where we study the limitations of existing kernel debloating techniques, and share our insights of how to make kernel debloating more practical. This figure shows the lines of code for a Linux kernel per kernel version. By now, Linux has more than 20 million lines of code, and it still keeps growing. So the commodity operating systems are bloated. OS bloat are due to the fact that new software features and hardware support are introduced. At the same time, Linux has tremendous amount of legacy code. Our study finds that most applications do not need all the kernel functionalities. And bloated kernel could have problems including security and performance. For example, a larger kernel has a bigger attack surface, and unnecessary kernel code could bring down the performance. A recent trend of microservices and function as a services emphasizes the problem of OS bloat, because in such contexts, virtual machines are intended to run small and simple applications, and large parts of the kernel are not necessary. So the concept of config-driven kernel debloating is that given an application and its workloads, we try to select only necessary kernel config options. Config-driven debloating is the de facto technique because it does not modify the kernel code and generate stable kernels. Also, it's widely supported by the community. However, handpicking necessary options from thousands of options is impractical, and the incomplete and poor kernel documentation is also an obstacle. Kernel configuration options controls what part of the code is compiled into the kernel by language preprocessor hints at different levels, including statement and function. Kernel configuration options also appear in make files, controlling the code at object level. This is an overview of how kernel-driven kernel debloating works. First, trace the kernel running target workloads and analyze what part of the kernel are used. Then, correlate the kernel parts with configuration options. And finally, compile the debloated kernel with the options. This paper presents 5 limitations of configuration-driven kernel debloating techniques, and we designed a tool named COZART that addresses some of the limitations. Finally, we present 6 insights of kernel debloating that we have learned. Among these limitations, 3 of them are essential. Essential limitations are inherent in the nature or assumptions of kernel debloating, including the difficulties to obtain complete kernel coverage for applications, and the inability to distinguish what is executed and what is needed. On the other hand, the remaining 2 limitations are accidents that are the flaws of existing approaches, including no visibility of kernel boot phases, no support for fast application deployment, and an adoption of coarse-grained tracing. These 3 limitations are addressed by our tool, COZART. In this paper, we designed an advanced kernel debloating tool called COZART that we use as a vehicle to conduct our studies. COZART is a fully automatic tool and produces stable kernel. Also, COZART can debloat kernels within tens of seconds when workload changes. We also validate that COZART does not change application's behavior. So COZART divides the configuration into configlets for the deployment environments and applications. Configlets are a set of configuration options. Baselets are configlets for different deployable environments, and applets are another type of configlet that support applications. So These are examples of a baselat for a Firecracker hypervisor and an applet for Apache web server. COZART tracks the configuration options at the offline phase. We patch QMU to trace the program counter and map PCs to a corresponding statement in the source code to understand what kernel module is used during the kernel execution. Using a full system emulator enables us to trace the boot phase, which is critical to produce a stable kernel. Also, loadable kernel modules need additional handling since they are not part of the kernel binary, and they are now loaded into memory at a fixed address. Config.lets are generated during the tracing process. A lemma program marks the end of the boot phase. Hardware-related options forms the baselets, and the remaining options are applets. When config.let are prepared, COZART builds the kernel by combining and composing config.lets. COZART also leverages the incremental build features to speed out the kernel building process by only building things that needs to be rebuilt. This diagram shows how COZART works in the pipeline. COZART takes 3 inputs: kernel source code, vanilla kernel, and application workloads. Then, config tracker would trace the application, find out what part of the kernel are used, and correlated those parts with kernel configuration options. And then, config.let generator produce config.lets and store them into a database. And all these steps takes place offline. In the online phase, kernel composer composes config.lets and store in the database and generates the final configuration. Kernel builds use the final configuration to compile the debloated kernel. So now let's take a look at evaluation. We evaluated boot times, application performance, memory savings, kernel size. We also validate if the debloated kernel changes application execution. We use both benchmarks and test suites for 6 popular applications. Our baseline is Ubuntu kernels since it's the most popular distribution in cloud servers. We also apply COZART to other types of kernels, such as L4 microkernel and Amazon Micro VM. This is the machine setup for the evaluation and the implementation details for COZART. So for the obvious reduction result, this table shows the kernel reduction for applications. We measure the number of kernel modules and kernel size reduction for both static kernel modules and loadable kernel modules. COZART is able to reduce the kernel effectively. The similar reduction result is because all these deployed kernels are deployed as KVM virtual machines, and they share the same base rate. Debloating kernel does not only improve the security, but also performance. We see improvements in boot times, application performance, and memory saving. Besides reducing the kernel, we also need to ensure that COZART does not alter application's behavior. Therefore, we validate by checking the log messages and application test suite coverage results. During evaluation, we did not see any differences in output or error messages. We run test suites for applications on the vanilla kernel and the debloated kernel. We show that the coverage of debloated kernel matches the vanilla ones. We also do this comparison using benchmarks, and we get the same coverage. But when comparing the coverage results, benchmarks are much worse than test suites at testing application behaviors. Finally, I would like to share 6 insights that we have learned. First, in kernel tracing methods are initialized too late, and they are unable to observe the boot phase. Boot phase is very critical to produce stable kernels. Second, kernel debloating can be done within tens of seconds. By using config.lat, COZART can remove the tracing, which is the most time-consuming stage, out of the critical path. And leveraging the incremental build feature, a new kernel can be generated within tens of seconds. Function level tracing does not address all the kernel configuration options. COZART uses instruction level tracing to control intra-function features. Existing kernel debloating techniques rely on tracing. Ideally, applications should be 100% exercised during tracing. However, we found that test suites coverages are not as high as expected, and benchmarks are much lower. Combining benchmarks and test suites can alleviate this problem to some extent. We discovered an essential limitation, which is the inability to distinguish used but not necessary modules during tracing. And domain-specific information can help to remove such options. For example, if we know that we are going to deploy the kernel on a Zen machine, then we can use Zen config as a baselat, and this baselat can help us further reduce the kernel by 40%. Finally, we found that config-driven debloating can also effectively debloat other types of kernel. We apply COZART to other kernels and see a 47% reduction for L4 microkernel and a 20% reduction for Firecracker micro VM. So this is the end of my talk. Thank you very much.